Hi everybody, I just want to walk through the Northern Shoveler Coordinate System Lab really briefly to talk about why we might pick a particular projection over another. First of all, let's look at the attributes. I just want to show you the latitude and longitude values in here. So you guys know that you plotted up two different data sets from one table of data. So we have all the different birds. We have where they were banded and where they were recovered, and then information about those particulars. But look at how small these numbers are relative to the UTM easting and northing values that we're used to seeing. They're all small, they're all less than 180 in absolute value, and that's what indicates that these are in latitude and longitude. This is 50 degrees north of the equator, 33 degrees north of the equator, and then 111.6 degrees west of the the prime meridian, 86 degrees west of the prime meridian. So these are degrees, meaning they're angles coming out from the center of the Earth, equator north. We're talking about that angle. So what coordinate system these belong to, you don't know for sure. Chances are it's probably the North American datum of 1983 or WGS 1984. And I told you in the lab instructions that it belonged to North American datum of 1983, but you know it's going to be a geographic coordinate system. These are latitude and longitude, and that's the same thing as a geographic coordinate system. That's where we have to start. So when we plot up this data, we need to put in our banding longitude and our banding latitude, and then we need to put in a coordinate system. This is defaulting to the wrong one. It's pretty close, but close isn't good enough in GIS. So we'll go down here and pick North American datum of 1983. Okay, so here's Alaska, Canada, and the beginnings of the United States, the continental United States. Let's go up and plot up the recovery data while we're at it, recovery longitude and recovery latitude. And now we have the correct coordinate system. Oh no, we don't. We'll do that again. It's because the data frame is set to WGS 84 for some reason. Okay, so there's our other data, too similar of a color applied to it. All right, so banding and recovery data from one data set. Now, let's go ahead and set our coordinate system here so that it matches, so that we don't have any misunderstandings. Doesn't matter. But now, with layers set to the North American datum of 1983, we can make a copy of these data and piggyback the coordinate system off the data frame. Or we can use the source data because we set these correctly. It doesn't really matter, but know that these are just temporary sketches. They don't have a coordinate system, they don't have an attribute table. They're just kind of a quick sketch to see if they're in the right place. So we need to do the trick of exporting them this way. We could also project the data using an actual tool, but this is so fast and easy. We want to export all the features using the coordinate system of either the source data, because we did that correctly, or we could use the data frame in this case, because I just set that to the North American datum of 1983 as well. Get in the habit of using this folder, because unless you set your Scratch output workspaces to a geodatabase, it's going to do this. It's kind of going to try and force you to stick it in the geodatabase, and so let me just make a quick temporary output folder, and we'll call this is our recover data. Yes, I want to add it to the map, and then we'll do the same thing with our banded data, export data, and that can all be left the same. Here I can just put banded because I can see it's going to the right place. Okay, Now, I've just replaced both of these data sets with new good data. I'm going to remove this so I don't get confused. If I go in and look at the properties here, not of V layer, I've maintained that I've got these relatively small numbers, and now ARC knows they're in degrees, and my coordinate system is a geographic coordinate system, North American datum of 1983. And that should be the same for both. We can test whether or not they're correct by adding a base map. And there we go. Now sometimes this will plot up just right when you go to change the display coordinate system to something else, something projected. Your data, one of your data sets might go away, or maybe both. They don't actually go away, they collapse down to one little point. And I can demonstrate that too, but let's just plot ahead here and decide what kind of coordinate system we want to apply here. If we're trying to measure migration distances between, you know, a bird that maybe migrated from Alaska down to the southern US, we're interested in measuring distances over the extent that covers all of North America. So I think there's two important things to know about coordinate systems. They cover a spatial extent, and they try and minimize distortion over that geographic extent. And then there's usually some kind of metric, especially for large scale, large spatial extent coordinate systems. They can kind of strive mathematically to reduce distortion in certain measurements at the cost or expense of others. So the kinds of distortion I'm talking about again are, you know, area calculations, distance calculations, shape and angle. Can't think of the fourth one off the top of my head. Distance, I guess. So that'd be distances, areas, shape, and direction. Yeah, so those are the four. So if we are looking for one over North America and we want to preserve distance measurements, we really don't have a whole lot of choices. If I go up to layers, to the properties, and we take a look at the coordinate system tab, just first of all know that there's a favorites folder, and then we have all the coordinate systems that are geographic organized in one folder and all the projected ones in another folder. We definitely want a projected one. And you can dig through here all you want. I tried to point you in the right direction that you want to get into the continental. But if you don't know anything about ARC, Google it. It's a kind of a strange coordinate system that's designed for raster tiles for stitching together imagery. So there's nothing really appropriate here. County systems doesn't make sense. That's too small spatial extent. Gauss-Kruger, that's not going to help us out. You can take a quick look here and kind of realize that's not helpful. National grids, okay, maybe. So if we go down to North America, you'll find datums for Mexico, Guatemala. None of these are in North America, so that's out. By that I mean it's not covering Alaska down to the continental US. So national grids won't work. Polar, state plane, state systems, tribal, UTM, world. I mean, maybe UTM you could convince yourself that maybe there's something in here, but from UTMs you know that they're small bands and they're not going to work for, you know, entire continental coordinate systems. And then world, these are all just world, so that's too big, and the distortion over North America isn't necessarily going to be preserved. So that's why I stuck you right into the continental, and then we can go into North America. And then if you look through here, we really don't have that many choices. Alaska, Canada, Hawaii are too focused. You know, if our data may be centered around Canada, but as we move away from there, distortion is going to increase. US contiguous, that's just the lower 48. As we move away from there up to Alaska, distortion is going to increase. There are three in here. The North America, maybe arguably the US national, but not knowing that you'd have to just intuit that equal area is going to be preserving area calculations, and we're still focused on distance. And so North America equidistant conic, this guy, equal area, preserves area. Conformal, if you didn't pick it up from the lecture material, you could Google it. These tend to preserve shape and angle. And so we really are just left with this one coordinate system. Now, if you go and measure our bird, and you try measuring our bird in a whole bunch of different coordinate systems, you might find a coordinate system that gives you a closer distance, closer to the geodesic than North America equidistant conic. But I would argue that that's just luck for that one bird, and maybe not applicable for an entire data set. Why wouldn't we just keep it in geodesic? Good question. For distance measurements, we can. Manually, we can do that, and we could probably just leave it in the geographic coordinate system and make those geodesic measurements. But for things like area and most of the other applications, especially if we were dealing with rasters, the projection is absolutely critical. It's just easier to demonstrate with this point data than it is with rasters. And because we do so often work with rasters, learning how to choose a good coordinate system is really vital, and this is just kind of an easy way to demonstrate it. So with this point data, we could probably do something else, but for the purposes of the exercise, North America equidistant conic is a sound choice. Yeah, so that's it. If you have questions about that, let me know, and I'll talk to you next time.